Understanding buffers actually is going to help us with our titration calculations. And again, the goal here is just to be able to find the pH at any point in the titration. If you add any amount of acid to any amount of base, I'd like you to be able to figure out the pH. Now, we're going to focus our titration analysis, our acid and base analysis, to 4 possible scenarios. They're called strong acid plus strong base plus strong acid, weak acid plus strong base, and weak base plus strong acid. The nomenclature here is kind of important. The first thing listed is what you start with in the beaker, in the little Erlenmeyer flask. And the other thing, the second thing listed, that's what's in the burette. So in the SA plus SB, strong acid plus strong base, you would have an acid down below and you'd have a base in the burette. So you'd slowly add in the strong base to the strong acid. Now, if you have 2 strong systems coming together, we saw in the last chapter that the pH should be about 7. So the equivalence point should be about 7 for strong acid plus strong base. Now, the second one, we're starting with a strong base in the beaker under the burette, and we're slowly adding in the second part, the strong acid. So the strong acid is being added to the base. So that solution will start basic, because that's what the first part is, and it will get more acidic as you add more strong acid. But strong bases plus strong acids should also have a pH equivalence point of about 7, and that'll be a nice way to see it. Now, we're also going to look at if you start with a weak acid and you slowly add a strong base to it. Now, weak acid plus strong bases, we saw in the last chapter, the equivalence point will actually be slightly basic, greater than 7, because when the moles are equal, all of the weak acid will have turned into a weak base, and bases make the pH get greater than 7. And then finally, we'll look at weak base plus strong acids, where you're starting with a basic solution, and it's getting more acidic as you add strong acids. The equivalence point we saw in the last chapter, a little bit less than 7, because when the moles are equal, the weak base has been turned into its conjugate acid. Acids make pHs a little bit acidic. These titrations, all 4 of these titration types, we're going to separate them into regions, and each region will have its own pH formula, and the pH formulas will repeat. So we're going to see that some of the SA plus SB equations will be used in the SB plus SA region. Buffers do become important when you have weak acids plus strong bases and weak bases plus strong acids. So we will use equations like the Henderson-Hasselbach when we get to those particular regions. In the lab, there's a titration calculations lab we're going to do, and that's going to give a lot of practice with all 4 of these types of titrations. So I'm hoping that these notes will augment the lab notes and the lab lecture a little bit more. In addition, there is a titration guide on the website that you can use for different regions to see what's happening. So let's talk about these 4 types of titrations. When you're doing these, remember that strong acids and strong bases annihilate their opposites. In a chemical world, which doesn't really use an annihilate, we would say that it makes the K of the reaction very product favored. We're going to assume to use one-sided arrows for those. So strong acids and strong bases don't coexist very well, shall we say, with anything. Weak acids and weak bases, though, do produce their conjugates, and this is what leads us to buffers and some weird pH effects at equilibrium. And those will also be important as we go through all of this. Ka and Kb can be determined through titrations. So there's several different ways to figure out these Kas and Kbs. But in this lab, we're going to look at how people calculate these equilibrium acid and equilibrium base constants. It's a really nice way to do it. If you have discovered a new weak acid or weak base, you can use a titration to actually figure out what the Ka and Kb values will be. Ka times Kb is always equal to Kw, assuming that they're conjugates. That also assumes that you're at room temperature. And again, in this class, we're basically at room temperature. If you do research with acids and bases in medicine, you may need to reconfigure because the body is not at 25 degrees Celsius. pKa and pKb can be helpful. Remember, pKa is minus log of Ka. pKb is minus log of Kb. And pKa plus pKb also equals 14. 14 if they're conjugates and you're at 25 degrees Celsius, just like pH plus pOH equals 14. You almost always need to know the initial concentration and volume of the titrant. Sometimes you can calculate it, but almost always you need to figure this out. Sometimes it'll be given to you, and sometimes you need to figure it out. You can also figure out the amount of titrant needed to reach equivalence, and we'll talk about these as we go through this section.
When a molecule of hydrogen chloride and a water molecule encounter each other, they react to form a hydronium ion, H3O+, and a chloride ion. When sodium hydroxide enters the solution, it splits into sodium and hydroxide ions. The hydroxide ion and the hydronium ion react readily with each other to form two molecules of water. Sodium and chloride ions are left in solution.
In a strong acid, strong base, the spectators just kind of go away. So for NaOH, that would be the Na+, and for HCl, that would be Cl-. They don't affect pH, so they just kind of hang out on the side. It's really the interaction between hydronium and hydroxide that gives all this power, if you will, for these reactions. So down below, I have kind of a cheesy graph that's from a strong acid, strong base titration. And you can see that it's kind of like an S-curve, all right? And the S-curve is something that sometimes people talk about with these. When it comes to strong acid, strong base titrations, there are 4 regions that you need to think about. One of them is the initial region, i.e. when you only have what you start with, which in this case is a strong acid. One of the regions is called the equivalence region, and that's where the moles of what you start with equal the moles of what you're adding. And so the moles, which is the symbol N, moles of strong acid equal moles of strong base, and for these the pH should be about 7. Then there is the pre-equivalence region, where the moles of what you start with are greater than the moles of what you're adding. And then finally, there's the post-equivalence region, where the moles of what you're adding are greater than the moles of what you started with. Now, each of these has an equation, and we'll talk about that in just a second. At equivalence, the pH of a strong acid plus strong base titration should be, and there's 3 possibilities. Well, on that graph like there, you can probably see that the pH was equal to 7. Strong acids and strong bases annihilate each other. They totally knock themselves out, and if you're at equivalence, the moles are equal. So the products will be water and some kind of neutral salt. So you could have like sodium chloride and water if it was HCl and NaOH. Nothing affects the pH. pH should be 7 for strong acid plus strong base titrations, as well as strong base plus strong acid titrations. The 4 regions of strong acid plus strong base are initial, pre-equivalence, equivalence, and post-equivalence. Now initially you have just the strong acid, so pH equals minus log concentration of the strong acid. But we're going to see, because there's so many moles things here and volumes, sometimes it's good to think about them in terms of moles of strong acid over volume of strong acid. So either way is fine. Now at the pre-equivalence region, you still have more strong acid than you have the strong base you're adding. So the equation is overall minus log NSA divided by total volume. But you have to take out the moles of strong base that have been added, because those moles of strong base go after the strong acid. NSA minus NSB is still a number larger than 0. All right, so it's not going to 0, but it is, you have less moles of strong acid than you had. And in the bottom part, you have to use the total volume. Concentration is always moles over volume, so you have to take into account both the volume of strong acid plus the volume of strong base added to that point. The equivalence point for strong acid plus strong base, as well as strong base plus strong acid, is going to be 7, and that's kind of cool. Now, on the titration graph, you can see that volume is usually the x-axis, and pH is the y-axis. So if you didn't know what was happening here, a lot of times you can identify a strong acid plus strong base by literally looking at that steep point of the curve, where the equivalence point is. And if it's about 7, you've got a strong acid plus strong base. Strong base plus strong acid would start basic and go acidic, so it would also have an equivalence point of 7, but be an opposite S-curve. We'll see that in a little bit. Post-equivalence means now that you have more of what you're adding than what you started with. So that means for us here, more base relative to acid. pH of a strong base, 14 plus log moles of base left over divided by total volume. So again, you've got to figure out moles of strong base that are excess. So you subtract NSA from the moles of strong base, and again, you divide by total volume. Now, in all these equations, NSA, the moles of strong acid, and VSA, the volume of strong acid, those are constants for a titration. Those numbers don't change. It's what you're adding second, which in this case is strong base, that will change. So NSB and VSB are going to change. You can usually find the VSB, the volume of the strong base, like from the titration graph itself. That's the x-axis. And then remember that volume of a strong base times concentration of strong base equals moles of strong base. So if you know the volume in liters and you multiply it by the concentration of the strong base, moles per liter, that's going to give you NSB, the moles of strong base. And that's what you'll do on these different problems. So if you kind of look back a little bit here, the initial equation and the pre-equivalence region are just when you have an excess of strong acid, all right? So minus log concentration of strong acid is how you'd find the pH. You have to take out the amount of base that's been added, but otherwise they're pretty much the same. Post-equivalence is the pH of when a strong base dominates. Again, you have to take out the amount of strong acid that was present, but it's overall the pH of a strong base. So I'm hoping that these equations don't look too crazy to you. Let's do a problem. Let's say we're titrating 50 milliliters of a 0.100 mole per liter solution of HCl with 0.100 molar NaOH. And it says, what's the pH of the initial solution? Well, let's break this down. HCl is a strong acid. It's one of the 5 strong acids we talked about in the last chapter. Sodium hydroxide is a strong base. It's one of the 3 strong bases we talked to. So the initial pH then is going to be the reflection of just the HCl. Well, HCl is a strong acid, NaOH is a strong base. This is an SA plus SB titration because we're starting with an acid. We haven't added any base yet. So it's going to be the initial region of the strong acid plus strong base titration. And if you have just a strong acid, pH equals minus log concentration. Oh yes, here's another advertisement. The other 4 common strong acids, HNO3, HBr, HI, HClO4, and the other strong bases, KOH and LiOH. Yes, we might see some of these in the future, so I'm reminding you here again of which ones they are and how I recommend that you memorize them. To find the pH, pH equals minus log concentration of the acid, the concentration of HCl, 0.100, minus log 0.100, 3 sig figs past the decimal because we put a 3 sig fig number in, pH 1.000. All right, so this would be like a problem if it wanted to find the pH of a 0.100 molar HCl solution. This is what you do, no problem. That's the initial point of our strong acid plus strong base titration. What's the pH after 45 milliliters of sodium hydroxide have been added? Okay, so now we've moved past the initial point and we're somewhere either pre-equivalence, equivalence, or post-equivalence. If you don't know, you can absolutely compare moles because all of those pre, post, and equivalence regions are all about the moles. But you can see in this problem, the concentration of base and acid are the same. So we can look directly at the volumes, 50 milliliters of acid and 45 milliliters of base. We haven't added enough base here to equivalate the acid, so this will be pre-equivalence. Let's do it the right way, though, instead of just my babbling way. First of all, you really should determine the region, and you're going to find the moles of strong acid and moles of strong base, and then just compare them. And if the acid moles are greater than the base moles, pre-equivalence. If the base moles are greater than the acid moles, post-equivalence. And if they happen to be equal, that would be truly the equivalence point. So what we're going to do is we're going to do that volume times concentration thing I mentioned earlier. We're going to take the volume of the strong acid in liters, 0.050 liters, multiply it by the concentration, 0.0050 moles of HCl. And again, that number will not change for this lab. We'll do the same thing for moles of strong base, 0.045 liters times its concentration, and as we talked about, 0.0045 moles of NaOH. So the moles of strong base are less than the moles of the strong acid we start with. So NSA, moles of strong acid, greater than NSB, moles of strong base. This is going to be a pre-equivalence region calculation. Those numbers, the moles once again, pre-equivalence minus log, parentheses, and the top NSA minus NSB, and on the bottom, and make sure you put parentheses around the bottom, especially VSA plus VSB. And you should use liters, by the way. So there's the moles on the top, total volume on the bottom. The moles part, you end up with just 1 sig fig. So the pH here, minus log of all that, 2.3. Just 1 sig fig, 1 digit to the right of the 3. Don't be too worried about that part. If you can see how to plug and chug into these equations, that's the cool part. The next question says, what's the pH at the equivalence point? So equivalence means that moles of acid equal moles of base. The two things you're looking at are the same value. At equivalence, HCl and NaOH are equal moles. They've knocked each other out. And in the process, they make water, a lot of energy, but they also make sodium ions and chloride ions. Now, sodium and chloride ions are some of the pH neutral ions we looked at in the last section. They don't affect pH. All of the conjugates of strong acids and strong bases don't affect it. So that would also include nitrate, potassium, all that kind of stuff. Sodium and chloride have no effect on pH. Pure water has a pH of 7. So that's why we say that at equivalence point, you should have a pH pretty gosh darn close to 7, all right? Because water is the only pH generating species, and water has a pH of 7. That's what you should have here too. Sometimes it's nice to know the volume required to get to equivalence, and you can absolutely do that. Remember that equivalence means that moles of acid equal moles of base. So in this problem, we had this many moles of HCl. We can cancel out the moles of HCl, turn them into moles of NaOH. We can then divide by the concentration of NaOH, and sure enough, it comes out to be, big surprise, 0.050 or 50 milliliters. Now for this problem, that probably seems a little silly because as we talked about, the concentrations are equal, so the volumes would have to be equal to get to moles. However, if the concentrations were not equal, this may not be as obvious. So you can do this kind of process. Moles of acid can be turned into moles of base, and then volume of base using concentration. FYI to the wise. So now let's figure out the pH when we've added 55 milliliters of sodium hydroxide. Now, we saw in the last problem that it took 50 milliliters of sodium hydroxide to reach equivalence. We are now past 50 milliliters. We are definitely into the pre-equivalence region. So knowing that, and from before, the moles of strong acid, 0.0050, we can figure out the moles of strong base at this point. So the concentration, 0.100 times the volume, 0.0055 moles strong base. And this number is definitely bigger than this number right here. That means we're now in the post-equivalence region. The strong base is dominating. So this equation, pH equals 14 plus log, basically hydroxide, but we want to find out the net moles of hydroxide left over after the acid's been removed, divided by total volume. Logarithms get really nervous when you have zeros and negative numbers in them, so that's why we're trying to always get these values. So NSB minus NSA is a positive number. We'll divide it again by the total volume, pH 11.7. So notice how the pH jumped quite a bit there. It started at 7 at equivalence and jumped up to 11.7. These strong acids and strong bases have very sharp S-curve graphs. This is what the graph would look like. Woohoo! So anyway, initially we saw the pH of this graph was a 1.00 value, and it is. We then saw that about 45 milliliters, the pH was only up to 2.3. And again, 45 would be about there, so you can see what's happening. So not a lot of pH change up to even 45 milliliters of strong base. However, when you get to equivalence, then you jump quite a bit. pH jumps to 7. And that's because now all the acid's been knocked out and the base is also knocked out too, so you have just pure water. And then just a little bit more base past that at 55 milliliters, pH jumps to 11.7. So this is the kind of process you can do. You can take the raw values, you can put them in a program like Excel or Apple Numbers or Google Sheets, something like that, plot them out. Y-axis would be pH, x-axis is usually volume in milliliters. Kind of cool. And you get to see the S-curve. Woohoo! Strong base plus strong acid titrations are very similar to strong acid plus strong base. The difference, though, is that, of course, you're starting now with a strong base, so the pH is basic. And then as you add the acid, the pH begins to go down. Equivalence point, where the moles are equal, will still have a pH of 7. Post-equivalence now will be acidic, and pre-equivalence now will be basic. But the equations are almost identical to what you saw for strong acid plus strong base. Initially, it's a pH of a strong base, so 14 plus log concentration of base, or if you want to write it in moles and volume, 14 plus log NSB divided by VSB. Now on this problem, NSB and VSB are not going to change. We're adding a strong acid, so NSA and VSA will change, but NSB and VSB will be constant. In the pre-equivalence region, you still have the strong base dominate, but you do have a little less kick because the strong acid has removed some of the strong base. So NSB minus NSA will tell you the net number of moles of strong base left over, and you divide by the total volume. At equivalence, the two are equal to each other, so the only pH affecting species is water, so the pH should be a value of about 7. And then like we saw earlier, that in the post-equivalence region, what you're adding is going to dominate over what you started with. So in post-equivalence, moles of strong acid will be more abundant than moles of strong base. Post-equivalence region pH expression is the same as the pre-equivalence region expression in strong acid plus strong base earlier. So it's minus log, essentially concentration of hydronium. You want to find leftover moles of strong acid on top divided by total volume on the bottom. So notice that SB plus SA, pre-equivalence region here, this equation, that was the post-equivalence equation in strong acid plus strong base. And the post-equivalence equation in this slide is the same as the pre-equivalence equation on the strong acid plus strong base. Equivalence is the same, and the initial point is just now dictated by strong base versus strong acid. So hopefully by thinking these through, you can see the logic to where they all pop in. And again, some of the things will be constant, like moles of what you started with and volume of what you started with. On the other hand, what you're adding will change. So NSA and VSA will change here. They're pretty chill.
Hydroxide ion is a strong base. It can be consumed in the body with a weak acid, such as dihydrogen phosphate ion produced in the kidney. In the reaction, an H plus ion transfers from the acid to the hydroxide ion to form water and HPO4 2- ion, the weak conjugate base of the weak acid.
If you take a weak acid and you want to figure out its properties, what people will usually do is put the weak acid in like the beaker, it's what you start with, and they'll titrate with a strong base. So this is an example of a weak acid plus strong base titration. And again, like on the last examples, there's going to be an initial region, which in this case is only when weak acid is present. You'll have an equivalence point where the moles of weak acid equal the moles of what you're adding, moles of strong base. And then there will be a pre and a post-equivalence region. Pre-equivalence means you have more moles of what you started with than moles of what you're adding. Post-equivalence, more moles of what you're adding than moles of what you started with. But there are a couple of differences here too. Notice that there is a half equivalence point. And when you're dealing with weak acids, or weak bases for that matter, half equivalence is a great way to solve for Ka. It comes from pKa. We're going to see that pKa and pH are the same at half equivalence. Also, there's a very flat region kind of right in here, and they call this the buffer region. A buffer forms when weak acid reacts with strong base. The weak acid is turned into its conjugate base, So you end up with weak acid still left over, plus some newly created weak base. So the pH change in this region is usually very gradual, and they call this the buffer region. So we're going to use a buffer equation in the pre-equivalence region, which is kind of cool. So that pre-equivalence region has this weak acid conjugate base system. It acts like a buffer. Half equivalence is going to be really important to us. At half equivalence, pH equals pKa. So you can actually solve for Ka if you don't know it for your weak acid at the half equivalence point. And graphically, on a graph like this, you can tell what it is. Half equivalence, by the way, literally half the volume required to reach equivalence. So this point right here would be half of the equivalence volume, 25 milliliters here. This would be 12.5 milliliters. So the pH at 12.5 milliliters, that pH is going to equal pKa. It's pretty cool. At equivalence, the pH of a weak acid plus strong base titration should be, and there's all these different values. So in the last chapter, we thought about what happens when you have equal moles of weak acid and strong base. The strong base pushes the reaction to the product side, and if the moles are equal, which is what equivalence means, all the strong base and all the weak acid have been reacted. But the weak acid creates its conjugate base. And a conjugate base is basic. That's what a base is, all right? And bases always have pHs greater than 7. So at equivalence for a weak acid plus strong base graph, your equivalence point should be basic. So if you aren't sure if you have a strong acid plus strong base or a weak acid plus strong base titration, look at the equivalence point. Equivalence point for strong acid plus strong base will have a pH very close to 7. On the other hand, weak acid plus strong base titrations, equivalence points will be much greater than 7. They'll be actually basic because of that conjugate weak base that's the active ingredient at that time. So here's our weak acid plus strong base. Initially, the pH is just dictated by the weak acid. So minus log Ka times Ca, or Cwa is fine. That's how you would find the pH. Yes, it assumes that 100 times K is less than C. I promise in these kind of problems that it always will be, just FYI. So pH minus log square root Ka times Ca. Now, at the pre-equivalence region, where you have more moles of weak acid than moles of strong base, we're going to use a derivative of one of the Henderson-Hasselbach equations. It was the Henderson-Hasselbach equation where you added strong base to a buffer. And that was pH equals pKa plus log. And in the numerator, it was moles of weak base plus moles of strong base. And the denominator, it was moles of weak acid minus moles of strong base. Well, in a titration, you don't have any moles of weak base at all to begin with in these kind of problems. So NWB is not up there because it's 0, all right? And if you break it down, pH equals pKa plus log moles of strong base divided by moles of weak acid minus moles of strong base. This is an awesome equation to calculate the pH of these pre-equivalence region areas. You have to know pKa, which is minus log of Ka. NSB will be determined by the volume. Remember, volume times concentration is moles. NWA is the moles of weak acid. It hasn't changed since the problem began either. Pretty cool way to find the pre-equivalence pH. At equivalence, all right, all of your weak acid has been turned into a weak conjugate base. And if you remember the pH expression for a weak base, it was 14 plus log square root Kb times Cb. Now, I've rewritten Kb here as Kw divided by Ka because you may or may not have actually calculated Kb, but Kw, 10 to the minus 14th divided by Ka, that's one way to find Kb. Cb, the concentration of the weak base, all of the moles of weak acid at this equivalence point have turned into weak base. So NWA, I'm going to reuse that number and just plug it in right there. It's not really reflecting mole moles of weak base, but all of the weak acid has been turned into weak base. It's the same number. And I'm going to divide it by the total volume, volume of weak acid plus volume of strong base. So initially this equation looks pretty weird, but if you think about it as 14 plus log square root Kb times Cb, maybe it's a little better. And if it's not, I apologize. I don't know, stupid scientist, whatever you want to say. Anyway, I digress. Post-equivalence, we have more moles of strong base than weak acid. So this equation looks a lot like post-equivalence being in the strong acid plus strong base. Only thing I did here is instead of NSA, which we used in strong acid plus strong base, here I used NWA, moles of weak acid. So pH equals 14 plus log moles of strong base left over divided by total volume. If you can do these equations here, you've got this type of titration down. And again, like before, hopefully you know Ka, but if you don't, you can find it from the graph. We'll talk about that a little bit. Moles of weak acid will not change, and volume of weak acid will not change. And the moles of strong base and volume of strong base you can get from the graph, or volume times concentration, that kind of thing. Honestly, it's not too bad. Let's do a problem. This is a question where we have 100 milliliters of a 0.025 molar benzoic acid solution. Now, benzoic acid is a benzene ring, C6H5, with essentially a carboxylic acid group on it, COOH. I'm going to abbreviate this HBZ because that's too many atoms and stuff like that. This is the acidic hydrogen right there. The hydrogens on the benzene ring usually don't come off very easily. Anyway, benzoic acid has its own Ka value, 6.3 times 10 to the minus 5. It reacts with water. It makes the benzoate ion. Notice that that H plus is missing, so this has a -1 charge now, and also some hydronium. We're going to titrate this benzoic acid with 0.100 molar sodium hydroxide. So initially, let's find the pH of the initial solution. This is a weak acid. You know it's a weak acid because A, it's not one of the 5 strong acids. B, it has a Ka value. And all Kas less than 1 are considered to be weak. So this is absolutely a weak acid. So if it's a weak acid, minus log square root Ka times Ca, Cwa, whatever, minus log square root Ka, 6.3 times 10 to the minus 5, times 0.025, which is the concentration, pH 2.90. All right, so it is acidic. It's not super acidic because it's a weak acid, but no problem. Let's figure out the pH after 10 milliliters of sodium hydroxide have been added. Okay, so now we are no longer at the initial point. We should try and figure out if we're at pre-equivalence, equivalence, or post-equivalence. You can probably imagine based on how this is going, it's going to be pre-equivalence, but let's go through the steps either way. So you need to really figure out the region, and that's really done through the moles, all right? And the moles are the way to figure out if you're pre-equivalence, equivalence, or post-equivalence. And remember, moles are just volume in liters times moles per liter. So if you do that for the acid, the benzoic acid, it's 0.100 liters times 0.025. We have a total of 0.0025 moles of weak acid, benzoic acid. Moles of strong base, same idea, 10 milliliters, 0.01 times the molarity, 0.0010 moles sodium hydroxide. So you can definitely see that the moles of strong base are less than the moles of weak acid. This is a pre-equivalence region. All right, so we're going to use the pre-equivalence region equation from earlier in order to solve the pH here. This region now is going to be a buffer region. And what's happening here? The benzoic acid concentrate amount is going to be lowered by sodium hydroxide. So as an example, in this case, 0.0025 will be subtracted by 0.0010, and you'll have 0.0015 moles of weak acid left over. But that 0.0010 moles that were subtracted, that has turned benzoic acid into the benzoate ion. So 0.0010 is also going to reflect the moles of this benzoate ion. The conjugate base pops out as you add strong base to it. The strong base has knocked itself out, but there will be now weak base and conjugate acid. It's going to be like a buffer. In the pre-equivalence region, knowing it's kind of like a buffer, what I recommend is you use this version of the Henderson-Hasselbach equation. It's an equation where you're adding a strong base to a buffer. The moles of weak base was 0, so I didn't include that. But as you can see, then it's just based on pKa and NSB and NWA. Now, pKa minus log of Ka, that comes out to be 4.20. And if you plug those numbers in, you should get out a value 4.02. That's the pH when 10 milliliters of sodium hydroxide has been added. So it's kind of cool. Henderson-Hasselbach works really well. If you didn't want to use this Henderson-Hasselbach equation, you could go back and do the double ice, where you'd have an initial ice table for dealing with the sodium hydroxide, then you'd have a second ice table for dealing with the new buffer concentrations, the new acid and the new base. But hint, hint, I highly recommend the HH equation. Let's figure out the pH after 12.5 milliliters of sodium hydroxide have been added. Now, on the last slide, we saw that the moles of weak acid, 0.0025 moles, and pKa were 4.20. So let's figure out now the moles of sodium hydroxide. Moles of sodium hydroxide, 0.0125 liters times 0.1, 0.00125. So this is pre-equivalence, moles of base less than moles of weak acid. We're going to use the same equation, but if you pump all those numbers in, notice how the denominator of the log part, 0.0025 minus 0.00125, that comes out to be 0.00125. So you have 0.00125 on top, 0.00125 left over on the bottom. That's a log of 1. And in the logarithm world, log of 1 is 0. So notice at this point, pH and pKa are the same. If you can find the half equivalence point, all right, pH and pKa are the same. And that's kind of a cool thing. So you can see that the pKa, 4.20, equals 4.2 as well. Half equivalence region, pretty cool, because this is a nice way to find or verify what your Ka value is. From before, there's all the numbers we had, all right? When the moles of strong base are equal to half the moles of weak acid, that's really what the half equivalent region is. You can find it easily because the half volume to reach equivalence is also half equivalence point. And at this point, pH and pKa are the same. And that's a really cool thing. Anytime you can find Ka values, it's pretty awesome. The volume of titrant needed to reach half equivalence is literally half that needed to reach volume of equivalence. So in this problem, it took 12.5 milliliters to reach half equivalence. That times 2, or 25 milliliters, that's going to be the equivalence point volume. Now what usually happens is you know the volume to reach equivalence, and half that number would be half equivalence. But in this problem, it worked out good to go the opposite direction. That's cool. All of these things are fitting together. But if you can find the pH and pKa at that point, it can be really helpful. So let's find now the pH at the equivalence point. Ka still 6.3 times 10 to the minus 5, etc., etc. At the equivalence point, the benzoic acid moles and the moles of sodium hydroxide are equal. So at this point, we end up with sodium ions, benzoate ions, and water. Now sodium, pH neutral, boring. Don't have to worry about that. Water, pH 7. And that can be interesting, but the most interesting thing here is the benzoate ion. Benzoate, the conjugate base of benzoic acid, is a base. So we would expect the pH at the equivalence point to be basic when you're titrating a weak acid with a strong base. It's not from the strong base that it's basic, it's from the conjugate base. That's the only pH generating species outside of water at this point. So you can quickly tell in a titration graph if something is a weak acid or a strong acid. You look at the equivalence point. If the equivalence point is 7, neutral, strong acid plus strong base. But if that pH at equivalence is basic, then you've got a weak acid plus strong base. And remember, there's a lot more weak acid plus strong bases probably possible than strong acids plus strong bases. It's much more common to see a basic equivalence point. with the math, find the moles of weak acid once again, 0.0025. We did that earlier. Now, at equivalence, that's going to equal moles of sodium hydroxide, so 0.0025. If you didn't find the volume of the strong base yet, then you can find it this way. Moles of strong base divided by concentration strong base, 0.025 liters is the volume you need to reach equivalence. And we saw that earlier with a half equivalence, but this is a much more common kind of application where you know the moles and you can find the volume to get there, stuff like that. And once you found that number, you could take half of it to find half equivalence, etc., etc. pH at this point is like the pH of a weak base, 14 plus log square root Kb times Cb. We never talked in this problem so far, as you can see, about Kb, but we do have Ka. So Kw divided by Ka is what I put in right there, and that's what the Kb part is. Now, on the other side, the concentration of the base, all of the weak acid has been turned to a weak base, so that's why we're reusing the moles of weak acid number. We do need to divide by the total volume, so you need not only the volume of the weak acid, but you also need the volume of the strong base required to get there. If you do all of this, pH comes out to be 8.25. This should be a basic pH. Weak acid plus strong bases have basic equivalence point. Oh yeah. Once you go past equivalence, then you have an excess of strong base. All right, and if you have an excess of strong base, you're going to have something that looks like pH equals 14 plus log hydroxide. And of course, you have to figure out how many moles of hydroxide are left over. You have to divide by total volume, but that's kind of what this thing is going to look like. So at this point, 26 milliliters, 1 milliliter past equivalence, we will have an excess of sodium hydroxide. And if you want to absolutely confirm that, find the moles, which you should do anyway. Concentration times volume, 0.0026 moles, and we had 0.0025 moles of benzoic acid from before. So pH equals 14 plus log moles of strong base left over divided by total volume. You can see here's the moles of strong base minus the moles of strong acid. It's a non-zero number. That's good. You want to be positive. Divide by the total volume. pH comes out to be 10.9. So again, a little bit more basic than it was before, which is kind of cool. Here's a graph showing the weak acid plus strong base for the values we just used. Initially, the pH was acidic. It's a weak acid. It wasn't as acidic as usually as a strong acid would be, but it is still pretty acidic. Then you can talk about the pre-equivalence region pHs. So at 10 milliliters, that pH came out to be 4.02. We then went on and found the half equivalence pH, and that's kind of important. pH at that point equals pKa, so a lot of times a half equivalence point titration calculation is really useful. At the equivalence point, now with weak base, the benzoate ion dominated, pH should be basic, and sure enough it is. And again, if you look, just the graph, the steep part right here, the middle point, that's the number you want to use. And it is basic. It's larger than 7. So this is a way to visually see quickly, yeah, you've got a weak acid plus strong base. You know it's a weak acid because, again, it started acidic and it's getting more basic, all right? On the other hand, you can confirm it with the equivalence point there. And then finally, at the last point, 26 milliliters, the pH was 10.9, basic, because now the sodium hydroxide dominates. Good to go. As the strength of the weak acid increases or decreases, you will see a change to the S-curve properties. A true strong acid plus strong base has a really nice and sharp S-curve, if you will. But notice how Ka there is going from 10 to the minus 2 up to 10 to the minus 10. And the quote-unquote S-curve gets more and more flattened out. At 10 to the minus 10, it hardly even looks like a curve. Also notice that the pHs are hardly acidic at all. As the strength of the acid gets weaker and weaker, remember 7 is neutrality, a lot of the pHs actually end up being basic for these super weak acids. So sometimes the value of Ka will affect the curve of the graph, absolutely. You can also have a titration with a polyprotic acid, and this is something we'll do in lab. This is an example of using phosphorus acid, H3PO3. Now, phosphorus acid has actually 3 acidic hydrogens to it. So you can see here in this curve, here's one of the titrations. That's the first hydrogen coming off. And we also see the second hydrogen coming off, the second part of the curve. In theory, if you did it right, you could see the third one, although honestly, the last one is usually really, really difficult to see. So let's say you were titrating a polyprotic acid and you didn't know Kas and stuff like that. Well, what I would do is do the whole curve. You'd find the equivalence point to reach the first you would find the volume to reach the first equivalence point. In this case, it's 50 milliliters, it looks like. Half of that volume, or about 25 milliliters, that's the pH that equals pKa. And that pH would equal essentially pKa1. That would be H3PO3 losing a hydrogen to become H2PO3 minus. But if you keep titrating, you end up at the second equivalence point. And at that point, that's where your moles of base are equal to, well, actually 2 times the moles of base at that point would equal the moles of the H3PO3 you started with. Either way, that's the second equivalence point. The half equivalence point for that acidic hydrogen halfway between the equivalence points. So if it took 100 milliliters to get to the second and 50 milliliters to get to the first, the midpoint, or about 75 milliliters, that's going to be the pH that equals your pKa2. So just kind of keep this in the back of your mind. This might be helpful when we do the lab, the acid and base titrations lab. We'll be talking about pKa1 and pKa2. You can see how to find them. If you wanted to try and find pKa3, you can see that the volume distance between first equivalence and third equivalence, it's about 50 milliliters. Well, another 50 milliliters over here, that would be approximately where pKa3 was. In this graph, they didn't go that far. Usually it's very difficult to find the third one, but you could at least make a guess as to what it was going to be. Pretty cool.
When an antacid tablet containing sodium bicarbonate is dropped into water, a reaction occurs that produces hydroxide ions and carbonic acid. The carbonic acid decomposes to form water and carbon dioxide gas, visible as bubbles. The hydroxide ions react with acid in the stomach to produce water.
Weak base plus strong acid titrations are similar to weak acid plus strong base titrations. The difference here now is that, of course, you're starting at a basic pH, and as you add the acid in, of course, the curve becomes more acidic. Just like with the weak acid systems, you will have like an in-between kind of buffer region where this gradual change occurs. At the half equivalence point, pH equals pKa, which is kind of weird maybe considering it's a base, but remember that pKa plus pKb equals 14. You can solve for pKb and then Kb from there. So there's a lot of kind of neat things you can do. There will be an initial point where you have only weak base. There will be an equivalence point where the weak base and strong acid moles are equal, and then pre-equivalence, more moles of weak base than weak strong acid, and post-equivalence, more moles of strong acid than weak base. At equivalence, the pH of a weak base plus strong acid titration should be. Okay, this question is kind of similar to what we did earlier with the weak acid plus strong base. Remember that if you're at equivalence, the moles are equal. So moles of strong acid equal moles of weak base. So that means they've all wiped each other out. Strong acids and strong bases don't play well with others. But in the process of wiping out the weak base, a conjugate acid has appeared, and the moles of weak base will equal the moles of conjugate acid at equivalence. Well, acid means acid. That means pH is less than 7. So A should be the right answer. The acidic properties of equivalence in a weak base plus strong acid titration come from the conjugate acid of the weak base. It's not from the strong acid, it's from the conjugate acid of the weak base. It won't be super acidic, but it will be more acidic and stuff than you might think. It won't be equal to 7. If you have a pH of 7, that's only for strong acid and strong base titrations. So like before, there's all these different equations for the different regions. Initially, where you have just a weak base, pH equals 14 plus log square root Kb times Cb, or Cwb is totally fine. That shouldn't be a big deal, and that should look somewhat familiar to you. Now, in the pre-equivalence region, we're going to use pH equals pKa plus log, and we're also going to use a variant of Henderson-Hasselbach. In the Henderson-Hasselbach, when you add a strong acid, it was NWB minus NSA on top, and in the bottom, you had NWA plus NSA. In a lab like this, in a titration, you don't have any NWA. You don't have any moles of weak acid that you start with. So you can just assume that's 0. pH equals pKa plus log moles of weak base on top divided by moles of strong acid on the bottom. Moles of strong acid, by the way, are just the number of moles of conjugate acid that have been created. Also notice that because this is a base, you might start with a Kb and you might need to turn it into a pKa. No problem. Kw equals Ka times Kb, and once you have Ka minus log of Ka, etc., etc. You could also go Kb to pKb and then to pKa that way. It's up to you. Now, at equivalence, the conjugate acid of the weak base is octave, and the weak acid pH equals minus log square root Ka times Ca. So here Kw divided by Kb would equal Ka, but if you have Ka, just use that there instead. And then concentration of the acid, all the moles of weak base have been turned into acid. You need to divide by the total volume. Good to go. And then finally, post-equivalence is where the strong acid dominates. pH equals minus log NSA minus NWB divided by VSA plus VWB. That's a very similar equation to when you had the strong base plus strong acid post-equivalence. Instead of using NWB, I used NSB. Same thing. You're just substituting in the different values. When the strong acid dominates, it's always going to look something like that. Pretty cool. An indicator can be a useful tool in order to find out if a titration has reached equivalence. You must pick an indicator in the right range, all right? If you pick the wrong indicator for the range you're looking for, it won't be very helpful. And here's what I mean for that. Well, we're going to look in the next slide at a bromothymol blue, all right? And this crazy thing, bromothymol blue, is right there. And notice that the yellow to blue transition is about there. So if you go up here, the pH change is 6 to 6.5. That's about where the yellow color of bromothymol blue goes to blue. And if our equivalence point pH is in that range, then it would be really helpful because once the yellow goes to blue, you know you're good. But if you picked, say, for example, thymol blue over here, that has a pH change at about a pH of 2. That would not be very helpful for a transition where you wanted the pH change to be about 6 to 6.5. Here's an example of the color changes. A pH is of less than 6, they're kind of yellow. pH is greater than 7.5, they're kind of blue. And in that middle range, it can be kind of a mixture, like blue and green together. Blue and yellow together is kind of a green color. That's kind of what it looks like. This isn't the best picture of all time, but hopefully you get the idea. Here's a question. Which indicator do you want to use? Phenolphthalein, which is what the first one is, or methyl red? And we're looking at the graph here. And ideally, you want the color change to occur at the equivalence point. Equivalence point is kind of the big part for chemists, as you can probably see. So in this problem, you want the equivalence point to correspond to the color change. And the pH at this equivalence point is certainly less than 7. So in this particular problem, you would probably want to pick methyl red. Again, the steep part right there, that's the equivalence point. And methyl red turns in this part right here, that would be the best pick for your indicator. If you picked phenolphthalein, which by the way is a very common pH indicator for a lot of these things, that doesn't start turning color until a pH greater than 8, maybe like 9 or something like that. So in this problem, you would definitely want to use methyl red. Indicators are maybe not as important as they used to be because of technology. If you can graph pH changes versus volume, that's a better way to see if you're at equivalence and stuff like that. But sometimes it's nice to visually have that color cue to know that you've made the transition, so they can be kind of neat. That's the end of chapter 14, part 2. This was obviously a pretty crazy chapter. We looked at buffers and common ion. We went into Henderson-Hasselbach, and then we also looked, of course, at titrations. But after you're done with this, you should be able to find the pH at any point for any combination of acid and base, as long as there's no weak acid plus weak bases. That's a different story. Anyway, so it'll be all stuff you can do. I definitely recommend you check out the study guide, bulleted lists of the things that are important from this section. The concept guide will have worked examples of things to do. I have a thing on types of equilibrium constants if you forget about Ka, Kb, Kw, etc., etc. The titration guide will give you more information how to calculate these things. The buffers Henderson-Hasselbach guide will talk more about that, which is kind of cool. And after this slide, if you can look at these online, you'll see a slide also of important equations and also some end of chapter problems where the answers are given. If you get stuck on this material, please reach out to either me and or the Learning Success Center / Avid Center at Mount Hood. All of us are here to help you. This is all stuff you can do, but at first it can be a little bit weird. You need a lot of mathematical dexterity, but you've got it. We just have to pull it out of you, dust it off, and take it and show you that you can take care of business. And I mean that sincerely. All right, thanks for spending your time with me. Have a wonderful day and good luck with your study.